The field of statistics is constantly evolving, and with it, hypothesis testing evolves as well. So over time, it became customary to choose a significance level, some fixed alpha value. 0.05 and 0.01 were particularly popular. And then after that fixed significance level is chosen, then a critical region is selected accordingly that goes with that fixed significance level. But over time, people then said, what if I get some value and then I'm comparing it to my null hypothesis value and I'm looking at it and I'm saying, well, here's the probability of getting a value that's that large if, in fact, the null hypothesis is true. Well, knowing that probability is actually a really helpful thing. So knowing the probability that I get some value that is as large or as small or as extreme as the value I get, then that's something that's useful information. So it became common for people to use an approach that involved p-values. Now, the p-value approach has become pretty extensively adopted by users of applied statistics. Now, there have been moves away from the p-value approach as well, but as with just about every field, things are slow moving with statistics, especially in the fields of applied statistics. And so it's still very helpful and useful for you to know the p-value approach. So what the p-value is it is the lowest level of significance, the lowest alpha value, at which the observed value of the test statistic is significant. So let's take a look at what the difference is between our approach to hypothesis testing when we have a fixed significance level or fixed alpha value and the p-value approach. So when using the classical approach, the approach to hypothesis testing with fixed probability of type 1 error, you're going to go through 5 steps. The first one is you're going to state the null and alternative hypotheses. The second one is you're going to choose a fixed significance level for alpha. So you're going to choose that value. Again, 0.05 and 0.01 are very common values to be chosen. Then you're going to choose an appropriate test statistic, and you're going to establish the critical region based on the alpha value. Then you're going to reject the null hypothesis if the computed test statistic is in the critical region. Otherwise, you're not going to reject it. You're going to fail to reject. And then finally, the 5th step is to draw scientific or engineering conclusions based on having rejected or failed to reject the null hypothesis. Now, if instead you take the p-value approach, you're going to go through 4 steps. The first step remains the same. You're going to state the null and alternative hypotheses. Then, second, you're going to choose an appropriate test statistic. Notice we're skipping the step of choosing a fixed significance level. So we're going to choose an appropriate test statistic. And then once we have that test statistic, we're going to compute the p-value based on the computed value of the test statistic. And then finally, you're going to use your judgment based on the p-value that you've gotten and your knowledge of the scientific system that is in question here, and you're going to make your decision accordingly. Now, let's take a look at the test procedure for a single mean, where we know the variance. Now, we can use the central limit theorem as long as our random sample is large enough. So, in that case, what we can do is we can define a critical region where we have a z-value that's equal to the mean of our sample minus the mean that is hypothesized for the population by our null hypothesis, divided by the standard deviation of the population that we know from the variance of the population, divided by the square root of the sample size. Now, our critical region is defined by that z value being greater than z sub alpha divided by 2, or less than negative z sub alpha divided by 2. Now the z's with the subscripts, so my z sub alpha divided by 2, that's defined the same way z sub alpha divided by 2 has been defined through everything we've done to date. So with that critical region in mind, we have if negative z sub alpha divided by 2 is less than z sub alpha divided by 2, then we do not reject our null hypothesis because our z value that we found is outside of the critical region we've defined. Rejection of our null hypothesis, of course, implies acceptance of the alternative hypothesis. The alternative hypothesis is that the population mean is actually different than my hypothesized mean. So mu, it does not equal mu sub 0. With this definition of critical region, hopefully it's clear to you that there will be a probability of alpha of rejecting the null hypothesis if in fact the null hypothesis is true. So my probability of type 1 error is in fact alpha. Also, hopefully it's clear to you how related to confidence intervals this is. So actually what this turns into is we're basically finding an 1 minus alpha times 100% confidence interval, and we're going to reject our null hypothesis if our sample mean falls outside of that confidence interval, and we're going to fail to reject if it falls within that confidence interval. Now, there's nothing special about this test with a single mean that makes that be the case. In fact, any of the tests that we do here, we can find these confidence intervals, these 1 minus alpha times 100% confidence intervals, and it will be the same as doing the hypothesis test with a significance level of alpha.